Hey guys, welcome to another AP Calculus AP exam review video. In this video, we will be looking specifically at questions dealing with solving differential equations with separation of variables, okay? So I understand that some of these you would be able to put into a calculator and get the answers that way, but the way the AP exam questions usually are asked, you have to still know your fundamentals as far as how to do the separation of variables pieces and solve the integrals of each sides and whatnot. So let's go ahead and begin. Notice we have two examples here. Okay, we're going to first start off with the dy dx is equal to x squared times this entire quantitative piece. And we have our initial value that is given here. Okay, so this is like our point that we're going to use to find our constant for c. Okay, so let's go ahead and first of all notice, remember when we separate our variables, we cannot integrate when dx, the respect to x piece, is in a denominator. So it feels like you are multiplying and moving over the dx to the right side. So basically getting your x's on one side and getting your y's on the other, okay? So if you have extra constants, it doesn't matter where you put those extra constants. But I would say from experience, they tend to be easier when they're left alone, whatever side they're on originally. So x squared dx, and moving my y's to the left, it's like I'm dividing both sides by y minus 1, will give me a dy over y minus 1. Now, this is the separation of variables piece, and now we're going to integrate both sides, okay? So integrating the left side, I know it's been a while since we've done this, but u substitution says y minus 1 is our entire u, so that du is just dy, okay? So if I'm looking at substituting this, this is like a form of 1 over u du, which is the natural log of the absolute value of u plus c technically, and then we would resubstitute this piece right here for u, okay? So the shortcut is, if your bottom piece is linear, well then it's going to be the exact replica as long as the coefficient of your variable is a positive 1, okay? So in this case, it's just going to be the natural log of the absolute value of what you see, y minus 1. And we're going to go ahead and take care of this plus c by adding it to the right side with the x squared pieces. Okay, so let me kind of keep this separated with equal signs like this. And then x squared is just a simple reverse power rule, x cubed over 3 plus c. Okay, so this is our general form. Right now, this is our general form because we don't know our constant for c yet. Okay, so we'll put general form. Okay, and we will get our particular solution once we use our initial value to help us find the c. Okay, and the way we're going to do that is we're going to go ahead and plug in our x value of 0, and we're going to plug in our y value of 3. So when I plug in 3 minus 1 is 2. The absolute value of that is still 2, so we have the natural log of 2. And then this is going to be 0 plus c. So we're just going to say c is natural log of 2, okay? So remember, just a reminder, whenever we have variegated variables inside of our natural log piece, we want to keep it as far as absolute value. But once we plug in and we solve, we can change them too. Once we have that constant inside that we solve the absolute value for, we can put parentheses, okay? So c, this is our constant, okay? So natural log of 2. So what we're going to do is we're going to put in this c. Let me go ahead and write it up here so we have it off to the side. Actually, I'll just go ahead and move it. So natural log of 2 is our c value. So I'm going to now change my general form into a particular form. Whoops. By substituting that in for our c value. So this right here is our particular form, but typically we like to solve differential equations by saying f of x equals our answer, or y equals our answer. Okay, so our goal is to get this y all by itself, and I'm talking about this one right here, and then we technically have our correct form of our particular solution. Okay, so let's go ahead and start getting y by itself. Well, I know if I apply a base of e to both sides, so this is like becoming ground level, if you will, these will cancel out to a form of 1, bringing down my absolute value piece, which is shown here. Okay, this next part is very, very important. A lot of people forget from Algebra 2 that this is e to the power of this entire piece right here. Okay, so quick review. We know that x squared times x cubed is equal to x to the 5th because we're adding powers because we're multiplying things with the same base. Okay, so those are exponent rules. Now, if I'm looking at x squared raised to the 3rd power, again, just quick review, then we know a power raised to a power, we would multiply. So what we're going to do is we're going to take something that kind of looks like this, and we're going to go backwards to create 2 separate pieces. Because technically, x to the 5th is x to the 2 plus 3. And that's what we see here. In the power, we see addition occurring. So if I wanted to break it up and go backwards into 2 separate monomials glued together with multiplication, I'm going to have e to the power of x cubed over 3 times, again, times, because this was addition, it'll go to times, e to the power of natural log of 2. Now, we know we can simplify this and bring the 2 down as a coefficient. So we could have 2 times e to the power of x cubed over 3 on the right side. And then on the left side, we have this absolute value of y minus 1 piece. Now, at this step, when we're almost done, we're going to go ahead and use our initial value condition to see whether or not this piece should be positive or negative. Okay, so let's test this out. If I were to plug in 0, plug in 0 where x is at, 0 cubed is 0, divided by 3 is 0, e to the 0 is 1, and then we would multiply by 2. So we have a positive 2. So right now we have a positive 2 that we know that this could be a plus or a minus as far as when we simplify. Well, in this case, it's going to be a positive. And notice why, okay? This will erase as a positive form of all of this, not a negative form, because when I move this 1 over, I'm going to have this plus 1 piece to it, okay? So plus 1, when I move this 1 over, would leave me with y all by itself. And now, because I chose to do the positive version of that absolute value, remember, this could simplify to a positive or a negative form of that y minus 1. I chose correctly with this positive because then it kept this as a negative 1. When it moved over to the right side, it became a positive 1, thus verifying when I plug in my 0 value here for x, I'd get 2 plus 1, which would give me the 3 that it said that I should get. Okay, so separation of variables, my final answer could be y is equal to the following, or you could put f of x is equal to 2e to the x cubed over 3 plus 1 down here. This would be our solution, our particular solution. Okay, so now let's go to our next example, okay? So let me take off a little bit of this scratch work so that you don't get confused, okay? And we have 6x squared plus 8, or times y plus 18x squared. Now, remember, when you do separation of variables, the most important thing is for you to identify where does the multiplication occur. See, I have 2 monomials right here that are separated, because technically over here, I was able to separate it because this is one huge monomial glued together with multiplication. I know the y minus 1 is a binomial by itself, but when you glue it together, if you will, through multiplication with another monomial, this entire piece is represented as one monomial. That's why you can break it up. Well, right now, we don't have that. We have a binomial. Okay, so we're going to do GCF. So we're going to, greatest common factor is a 6x squared, and we'd have y plus 3 left over. So now we've created what we had over here, one huge monomial instead of 2 separate monomials, okay? And again, they're glued together with multiplication that occurs right there. So dy dx is equal to this. This is our initial condition that we will use later. But now we know, we want to move the x's over to the right. So we have 6x squared off to the right, dx. We want to move the y values to the left, so we'll have y plus 3. And we just separated our variables, and now we're going to integrate both sides. The left side, again, because of what I said before, because that is a positive 1 coefficient and it is a linear function, there's no u composition or u substitution that we have to worry about with composite functions. We can go straight to the shortcut of whatever you see, put it in absolute value. Okay, so this is that natural log again. Okay, so now over here, I'm going to kind of interpret this as x squared dx, constant multiple ruled with a 6. We know this will become x cubed over 3. Okay, so, and then x cubed over 3 will multiply by 6, that constant multiple, and this will reduce to 2. So we have 2x cubed plus c, and this is our general solution. Okay, our general solution is general, again, because I don't know my c yet. Our goal is to get it to that particular by using our initial value. So let's plug in 1 here. We'll plug in -8 here. And when I plug in -8 plus 3, I get a -5. But when I take the absolute value of that, I will get a positive 5. Okay, positive 5, that 1 cubed is 1, times 2 is 2. So I have this for my natural log of 5 is equal to 2 plus c. So I could say c, if I move it over to the left, I could say c is going to be equal to the natural log of 5 minus 2. Okay? Now that I know what c is equal to, let's go ahead and plug it into our general solution right here, and then we can solve for our y and get our y all by itself. Okay? So let's go ahead and do that now. I'm going to go ahead and save a little bit of time by just copying this over. Okay, and then now I'm going to plug in this c value that we just found of this natural log of 5 minus 2. Okay, so it's like plus all of this. Okay, now this addition doesn't change the sign, so I can keep it as plus and minus. And this is what I have on the right side. Now remember, my goal is to get this y all by itself. I'm going to apply a base of e to both sides so that this right here is my entire numerator, or sorry, not numerator, power that is, and then this is my exponent over here. Okay, so we know that these will cancel. Okay, this natural log and this e cancel, and y plus 3 comes downstairs, if you will, on ground level. And now you have an addition and a subtraction. So we know addition pieces are 2 pieces of multiplication. So we have 2 to the x cubed times, or e to the power of 2x cubed times e to the power of natural log of 5. This subtraction piece right here, remember, it's whenever you're dividing. Okay, so it's like if I have x squared over x cubed, that's the same as x squared minus 3. Okay, so you're just subtracting the powers rather than adding, and that's just exponential rules from algebra 2. So this is going to be e to the second power. Okay, so now let's see a couple things. We know that these will cancel, and the 5 comes downstairs, if you will. And now you're left with this. You can have, you can rewrite it as 5 times, let me go ahead and rewrite it on the next line, 5 times e to the 2x cubed all over e to the 2. Now, you can move it if you want of resubtracting this 2 because it's the same. It's going to belong with this e base, okay? So either way, whether you subtract it or not, I'm going to go ahead and leave it in the power so that now I'm going to be working with this absolute value piece and see, is it the positive or is it the negative piece? All right, so here we go. Let's use our initial condition one more time to see whether or not it's going to be a positive or a negative. So we have 1 is x, and we have negative 8 is y. Okay? So, if I'm looking at this and I plugged in 1, well, then this would become 0, or e to the 0, because this would become 0, e to the 0 would become 1, and 1 times 5 is 5. Remember, my goal is to get a negative 8. Okay? So right here, I need to make the decision is this a positive or a negative? Well, in this case, it's going to be a negative form. And you can apply it to the left or the right side of the equation. Okay, so let me show you what's happening here. I'm going to say that this is either the plus or minus, like I did on the first example. And on this one, it's actually going to be the negative. Okay? Because right now, if I divide both sides by a negative, then I would get this negative 5 over here, and this would become y plus 3. So I'm almost done. I'm going to get y all by itself by subtracting this 3 to the right side, so that I would get something that looks like the following. All of this minus 3. Whoops. And this will make, this is our answer, or you could say f of x, okay, however you want to write it. But needless to say, this is our answer here that satisfies our initial condition. If we plugged in negative 1 for x right here, we'd get e to the 0 is 1. So we get negative 5 minus 3, of course, reflects that I would get that negative 8 that I needed. Okay, so it's all about when you take these absolute value pieces off, is it going to be the positive or the negative form? Over here, we saw that it was the positive form. Here, to make this negative 8 occur, we needed the negative form. Let's move on to our other examples. All right, so we have xy dy dx is equal to the natural log of x. Okay, so our goal is to move the dx's over to the right. So all variables of x will go to the right side. So I have natural log of x. I'm going to go ahead and divide both sides by this x, and then move the dx over to the right. Okay, we are going to take the integral of this, and what was left over on the left side was y dy. Okay, so now we have our two integrals that we're going to get ready to take the integral of, but we have separated the variables. Okay, so let's do the left side. That one's an easy one. That's just y squared over 2. And then the one on the right side, it's a little bit involved. I mean, I know you have calculators, whatnot this year for the AP exam, probably for questions like this, but it doesn't hurt to get that practice. U is natural log of x because du is 1 over x dx, okay? This 1 over x dx is right here. So we're going to say that this is u du that we're still needing to integrate. So we haven't taken the integral yet, okay? And if I do take the integral, I'll get u squared over 2 plus c, and now we're just going to resubstitute this back in for this u piece. So we'll have the natural log of x, quantity squared, over 2 plus c. This is what our antiderivative would in fact end up becoming. Now let's say that, again, we have the calculator, and you weren't sure of that, but you wanted to take the integral. You'd go and take the integral of the natural log of x, and you'd go over x in respect to x. Oops. And sure enough, you get that natural log of x quantity squared over 2, which is what we got over here. Okay? So let's keep going. We are now going to try to use our initial condition, x is 1, and our y value is negative 4, so that we can solve for our constant right here for c. So negative 4, be careful. Negative 4 squared is different than negative 4 like this squared, and this is the correct way we're needing to input it. So we have negative 4 squared will be a positive 16 divided by 2 is going to give us an 8. So let's go ahead and put 8 on the left side. Natural log of 1 is 0, and that's because we know that the natural log, and we can have the calculator, I understand that, but the key point is at 1, 0. Okay, yes, with the vertical asymptote at x equals 0 as well. That's just the natural log of x parent function. So 0 divided by 2 is 0, therefore c is 8. So I'm going to resubstitute this 8. I'm going to save a little bit of room. by putting it here, because that's what we found. Now, you would show all these steps. You would write all these steps because you're going to get points for all these different lines of work that you're going to show, must show on the AP exam. But for sake of time and sake of room, I'm just going to go ahead and finish it off from here. My goal is to get y all by itself, okay? So I look at this and I know that I can multiply both sides by 2 to get rid of this denominator. That cancels to a form of 1. And I can multiply this by 2. So that'll cancel and become natural log of x squared plus 16 is equal to y squared. Now, when I take the square root of both sides, remember, you must think of the positive or the negative form over here. It's very similar to that absolute value piece that we were looking at before, that plus or minus, okay? So y will equal natural log of x squared plus 16, and it's the square root, and we have to decide, is it the plus or minus? Well, this one will be the minus, because how else are we going to get this negative 4 if we retry our initial value? So let's plug in 1 for x. Natural log of 1 is 0. Square root is 0. Plus 16 is 16. Square root 16, we get a 4. Therefore, this has to be a negative in order to make that negative 4 occur. Okay? So let's go ahead and write it as this, or f of x, however you choose to do this. But needless to say, that is your solution. That's your particular solution. All right, so our last one, and then we'll start going to the forms of AP questions that you'll probably be exposed to, okay, on the actual AP exam. Last practice is right here. Let's get all of our x's and keep them on the right side again, because we cannot have this in the denominator. So we have dx, we'll have secant squared of 2x, and we're going to move our y's over to the left. So we'll have dy over y squared. Now, remember, like I said, wherever these other constants are, it's best just to use them. From my experience, it's best to leave them wherever they're at, okay? So I'm going to leave them on the right side, if you will, with the x's, okay? I'm going to go ahead and constant multiple rule it out because it is a constant. So integrating both sides, remember, it's only natural log of this is a positive 1 in this form, okay? Because you can't reverse power rule when this is a positive 1 because you can't divide by 0. Now, so this would become, if I wanted to rewrite this, again, I know that you will be able to use your calculators, but this is good practice. It would be y to the negative 1 over a negative 1, okay? And then secant squared of 2x. We have a little bit of a composition u substitution here. U is 2x, du is 2dx. So 1/2 du is going to be everywhere where dx used to be. So this dx where it used to be, I'm now going to resubstitute it with 1/2 du. Okay, so this 1/2 du multiplied with 4 is going to be 4 times 1/2 is 2 du. And then now we just have this u substitution piece that's going to be the rewrite of secant squared of u. Okay, secant squared of u, we know what that is. That's just tangent, okay? And we know that we're able to do that now because this coefficient of u is a positive 1. We can't do that up here, okay? It's only whenever that variable has a positive 1 coefficient. So this becomes the tangent of u multiplied by 2 plus c is equal to this over here, y to the negative 1 over a negative 1. Which, if I wanted to rewrite this, this would be a negative 1 over y. Because y to the negative 1 would go downstairs as a positive, and you still have that negative 1. Now, let's finish this off. The u substitution here was 2x, so I'm going to keep it in terms of x. Okay, and I got that from that u sub. And now I'm going to use my initial condition. So 1 will go where y is, which I already have it highlighted. And pi over 8 will go here where x is. That's why I resubstituted in this 2x so I could use this x value. It's not a u value as far as pi over 8. So pi over 8 times 2 becomes pi over 4, and the tangent or the slope at pi over 4 is 1. So we have 2 plus c is equal to negative 1 over y. And that y value is 1. So we're going to just say that this was negative 1. Remember, we were using our initial condition. So c is going to be a negative 3. Okay, so we're going to move this, and again, I'm just saving space. This will be a negative 3. Now, all of this can be y simply by flip-flopping this piece here with this entire piece all over here. Okay, it's like multiplying both sides by y and then dividing by this whole piece of 2 tangent of 2x minus 3. So if you do that by hand the long way, you're still going to get something that looks like this. Negative 1 over all of this piece is equal to a positive y. Okay, or f of x, but needless to say, this is your solution, the particular solution. And we can check it by plugging this in for x pi over 4. The tangent is 1, times 2 is 2, and then 2 minus 3 for the denominator would give us a negative 1. And negative 1 divided by a negative 1 does in fact check out to give us our positive 1 from our initial value. So this would be our answer. Now that we've done 4 practice problems, let's go ahead and go to one free response question that you'll probably see something correlated to this on the AP exam. Okay, so it says, the rate of the population of moose in a national park is proportional to this. Okay, and it says where t is in the time of years, m of t is the number of moose. So at time 0, there are 300 moose in the forest. Already, it's giving you what over here was written as an initial value. Our input is 0 and our output is 300, if you will. Remember, our input is t and our output is m at t. Okay? So now we are given a differential equation right here that shows m prime, if you will, dm dt. This is the first derivative. And it says y is equal to m of t is the solution of the differential equation. Again, with the same point that was given to us earlier is also reiterated right here. Part A is asking us to find the second derivative and use it to determine whether or not where we will have concave up or concave down. Which one would it be if there are 400 moose in the park? Okay, so we first have to look at the second derivative because we know the second derivative is positive if it's concave up, or its second derivative is going to be a negative if it's concave down. Okay, so we know that already. So we have to derive this f prime, if you will, this dm dt in order to get to this second derivative. All right, so let's go ahead and do that. Well, notice that this is a constant, so it's just saying the second derivative of m in respect to t is going to have this constant multiplied by whatever this derivative piece is. Okay, so the derivative here of this 800 minus m is simply going to be a negative dm dt. Okay, so all of that is just the derivative. Now we know, let me unhighlight it real quick. We know that dm dt, regular dm dt, is all of this. So I'm going to resubstitute that in because I want this equation right here in terms of m. Right now it's not in terms of m, it's in terms of m prime, if you will. Okay, so I'm going to resubstitute this back in so that I have nothing but m's and constants on the right side. Okay, so here we go. A negative dm dt. Okay, and that dm dt is going to be 1/2 800 minus m in parentheses, and this is what I have. So a lot of parentheses are happening right now, okay? And if I wanted to, is I can get rid of some of them, okay? So I could say this negative 1/2 multiplied with this positive 1/2, I could make it a negative 1/4 if I wanted to, okay? All of this would become a negative 1/4. And if you need to rewind just real quick to kind of see what just happened, feel free to do so, Okay, so this is my second derivative in terms of m. Now, it said when there are 400 moose, that means if I put it right here for 400, for m, because that's in terms of m, 800 minus 400 is a positive 400, times this negative is going to be a negative answer. It's going to be a negative 100. So we could say, let me go ahead and do this right here. We could say the second derivative when m is 400 will equal, well, again, 800 minus 400 is 400. Times 1/4 is 100. Times this negative is a negative 100. Okay? So we're going to say that the graph of B is concave down. And that's because we're going to say the second derivative is negative. And remember, whenever it's negative, it would be concave down. Okay? So now let's do part B. We're going to find y, or f of x. We're going to find our original function, okay, for the particular solution of the differential equation with the initial condition. So all we're doing is we're going back to our differential equation. We're using our initial value, just like we were doing on all of these other 4 practice warm-up problems, and we're going to finish this off. Okay, so let me go ahead and move on to the next slide to get a nice, clean start. Okay, so we're going to start with dm dt is 1/2, and this is going to be 800 minus m. Notice this right here with parentheses multiplication was very similar to these first 2 examples of how we created multiplication in between those pieces. Okay, so I'm going to go ahead and leave it as is and not distribute it. And then we're going to do the separation of variables, keeping in mind that our input of 0 and our output of 300 was our initial value. Okay, so here we go. We know that we have to get t's on the right side. So I'm going to leave this constant of 1/2 there, and I'm going to move this dt over, and then I'm going to move all of the y values, if you will, or the output values, which in this case has the variable of m, over to the left side. So I'm going to divide so that I have 800 minus m. I've separated the variables. I'm integrating, keeping that 1/2 on the outside since it's constant multiple rule. And now I'm ready to integrate. Okay, so the left side, now I know I told you that the shortcut was if this was a positive, that it's easy that you just do the natural log of the absolute value of whatever that denominator is. Okay, which normally you would say the absolute value of whatever this piece is, but because it's not a positive, either if you know the shortcut already, you could just write it as the carbon copy and then whatever that whatever that composition. In this case, it's a -1. You're going to multiply by that derivative, if you will, of the inside piece. Now, if you don't understand that, just go ahead and put u is 800 minus m, du is negative dm. So now negative du is going to go everywhere where you originally had a dm. So I originally had this, so the rewrite would be a negative du, okay? And then where it used to be 800 minus m, I would put u. Now you know that this piece is the natural log of the absolute value of u, but don't forget your negative out here. That negative is what I was talking about back here. Okay, so let me highlight it in a different color. This negative is out here. And now if I resubstituted it in my u, I would get this piece right here. Okay, so if you need to do the u substitution, by all means, show the work and do it. Otherwise, you can just know the shortcut. So the integral of dt is t. So it's 1/2 is a constant multiple rule multiplication plus c. Now I'm ready to use my initial condition. Okay, so let's go ahead and make some room here. And we're going to plug in our 0 for our input value. And then we're going to have 300 be our output value. So I have a negative natural log. Well, 800 minus 300 is 500. The absolute value of that is still 500. So I'll put parentheses now that it's a constant. 0 is going to be that. for t, so c is equal to this. Now to finish it off, I'm going to go ahead and put c is adding this negative. Okay, so let me go ahead and grab that and move it over here. Adding a negative is the same as subtraction, so I'm just going to leave it as subtraction. And now I just got to get my y, if you will, aka my output variable of m all by itself. Okay, so before we apply a base of e, we got to get rid of this coefficient of negative. So I'm going to multiply everything by a negative 1. That goes away and becomes positive. This becomes a negative, and then this one will become a positive. Every monomial piece I multiplied by a negative 1. Now, because natural log is a positive, I can apply a base of e. Now, this is ground level to both sides, where this is my entire exponent on my left side, and this is my entire exponent on my right side. Okay, I'm almost finished. We know that these will cancel, and the 800 minus m will come down, still with the absolute value. And because this is addition, we know that we're going to be multiplying between two bases that have e. We're going to have this negative 1/2 t, which you could put negative t over 2. And it's multiplied, because this was addition, with e to the power of natural log of 500. Well, from the practice that we've had so far, this will cancel out to 500. So that we have 500 is multiplied with this e to the negative t over 2. And now we have to decide, is this going to be a positive or a negative form when I simplify it out? Okay, I tend to always go for the positive, and if it works, then I keep it. Otherwise, I move it to the negative. So let's keep it as the positive. Okay, so the positive form of that is this, aka that, which doesn't change the signs. And then now if I wanted to get m all by itself, I could move it to the right, subtract this to the left, so I'd have something like 800 minus 500e to the negative t over 2 is equal to a positive m. Now our input variable is t. I'm going to go ahead and put t because it was asking me to write it in that form. Okay, like f of x, the way we were doing with our warm-up problems. And yes, you could have it written like this, and some of you are like, man, I actually like it whenever it's written on the right side. So either way, I mean, it's going to be the same thing. You could have m of t is equal to this written down here. So m of t is equal to that. Means the same as this, to each his own, okay? And yes, if I put in my 0 and 300, do they in fact check out? Okay, so let's see. 0 where t is at would give e to the 0 is 1. So 500 times 1 is 500. 800 minus 500 gave us a positive 300, and this did in fact work out. Okay, so that is the particular solution. And yes, you want to show all your steps, the separation, the integrals of each side, plugging it in. I know I erased it, but plugging it in to find your C value so that you could take that C value and change your general to the particular solution. Okay, so that's all we have.